All right, welcome back to the online Causal Inference seminar. Today we're excited to have Karthik Rajkumar from LinkedIn, who will talk to us about a causal test of the strength of weak ties. After that, as a discussion, we'll have Dean Eckles from MIT. Questions today will be handled by Georgia, so I'm switching over to her now.
Thank you, Dominic. Hi, everyone. So as always, please, if you have questions, submit them through Q&A. We do not have a collaborator today answering Q&A via chat. So please ask your questions as they arise so that when Karthik's natural pauses occur, we have the questions ready to ask. Also, please use the Q&A rather than the chat. If we have time, we might ask you to unmute yourself and ask your question live. In that case, you will be recorded. But if you do not want to do that, we will of course allow you not to. Okay, so now we're ready for the presentation.
Great. Thanks, Dominic and Georgia. Let me share my screen. Does it look good to everybody? Perfect. Okay. Well, thank you so much for this opportunity. I loved the online Causal Inference seminar right from when it was started. And so it's such a pleasure to come here and actually be on the other side. So the work that I want to talk about is the causal test of the strength of weak ties. I am at LinkedIn. My name is Karthik. And the central question that we're asking in this paper is what kinds of social networks matter for job mobility? This is work that I have been working on for over 3 years and in a fantastic team of academics and industry folks. We have Guillaume Saint-Jacques, who was at LinkedIn at the time of this work, Yevor Bojinov, who's faculty at Harvard Business School, Eric Brynjolfsson, faculty at Stanford, and Sinan Aral, who's faculty at MIT. This work was recently published in Science magazine. I will go over in this talk over essentially 5 main themes. One is why we're studying this question. This question is primarily an applied question, but there is an interesting methodological component. So I'll spend quite a bit of time talking about the methodology behind what was powering our analysis. And then after that, I'll go over the empirics of what we learned in terms of what kinds of networks do matter for job mobility. I'll go into a little bit more speculative territory in terms of what these empirics mean for the labor market. And I'll close with what I think are interesting areas for the literature to proceed from here, and also some of the other work that we do at LinkedIn. So why was LinkedIn interested in answering this question? At LinkedIn, our vision is to create economic opportunity for every member of the global workforce. We had 2 specific initiatives from which stemmed this question. One was our initiative on closing the network gap. We believe that 2 people with equal access to talent must have access to opportunity. But unfortunately, we know that in the real world, regardless of someone's skills, we see that people do have an advantage if they have access to the right networks. And so someone who had all of the credentials might still not have access to opportunity to the same extent if they don't have access to the right networks. And so LinkedIn was really interested in trying to address this gap. We had many programs, we still do. For example, we have the REACH program where we train and hire people from non-traditional backgrounds into our pipelines for engineering, recruiting, and sales. We also have the LinkedIn Coaches program where we get LinkedIn employees to try and mentor folks outside of their networks to try to bridge some of this gap. And of course, we were sponsoring lots of research in understanding what this gap is, what is the impact of networks on outcomes. And again, we also had another initiative called the Project Every Member, where we analyzed every new feature launch that we had at LinkedIn. As is traditional in industry, new feature launches are rolled out in an A/B test. And while A/B tests typically measure average outcomes, what we did with Project Every Member was measure distributional shift outcomes. So to see if outcomes increased in inequality or decreased in inequality because of a certain new feature. And we had dashboards based off of that. And of course, we had conversations with the owners of those respective products to shine light on what these mechanisms were for why inequality was increasing or decreasing and what we could do because of that. And then in terms of the academic literature, why is this an interesting question? Of course, The Strength of Weak Ties is a seminal work in the social sciences, one of the most cited papers of all time. It's a 50-year-old theory, very highly influential. And you know, over the course of the decades, weak ties have been argued to provide more employment opportunities. They provide more promotions, more innovation, more productivity. A lot of these studies were either on small data or non-experimental data. And so there was this big gap in the literature on trying to uncover this theory and explore it a bit further with larger scale data. There was work from Facebook that came out a few years ago that did do a large scale analysis that was correlational using Facebook data. And they found that strong ties, and I'll define what weak and strong ties are going into this talk, that strong ties were individually more valuable, although individuals tend to have a greater stock of weak ties, and therefore weak ties as an aggregate help better for job outcomes, but individually strong ties matter. But of course, from the causal inference point of view, network data is notoriously endogenous, and I'll talk more about that in the next section. And so when you don't have experimental data that's easy to come by, how do you know whether a certain claim that has been made is actually causal or not? And so that's where our paper came in to address this specific question that's been an important question that's been debated in the network science and sociology literatures for eons, and try to bring to it the scale of LinkedIn data that we have. Essentially, why do we need a causal analysis? I don't have to belabor this point to this audience, but just as a refresher, network data is notoriously endogenous. Here are a couple of plots of what the LinkedIn network looks like in terms of geography. We have average network outcomes across US states. On the left plot, we have average degree, which is the average number of connections that LinkedIn members have in that particular state. And you see that there's almost, there's definitely a 50% increase in terms of, the difference for the average number of connections that a member has in Wyoming versus, let's say, DC or New York. And then on the right plot, there's another measure of our members' networks, which is what we call diversity, which is essentially 1 minus the local clustering coefficient, a measure of, how many of my friends are connected to each other. And the higher the diversity, the fewer of my friends are connected to each other, which means I'm connected to a wider swath of the network, a more dispersed part of the network. And again, we see wide-ranging differences across different states in terms of these diversities. But so we already know that network data, is confounded on these measures of state. Of course, network data, it has a lot of homophily. People who are similar to each other tend to connect with each other. Some of these differences might be more obvious than the others. For example, occupation is a huge difference in terms of how networks manifest themselves. And since we're studying labor markets, this is an important thing to consider. Someone who's working in sales or marketing, for example, might have more dispersed and larger networks just by nature of their work, as compared to someone like me, perhaps, who doesn't have to interact with lots of different stakeholders all the time. And then industry is, of course, another big one. And that's not even accounting for personal attributes of people, such as, whether they're extroverted, whether they're naturally outgoing, and things like that. So there are lots of different reasons why networks are different of individuals across individuals. And so it's really important to try to think about a more causal way of looking at these questions. Luckily for us at LinkedIn, we have lots of experimental data, and in this plot, I'm showing you some of the experiments that we used for this analysis, and we had data across all these different states. What kind of experiments are we talking about? We were looking at what is known as the People You May Know product at LinkedIn. It was during the course of our analysis, what's called, I think now on LinkedIn.com, it's called My Network. Essentially, it is a grid of connection recommendations for new connections for our members to add. to their networks. These connection recommendations are powered by an AI algorithm. It's an ensemble AI model. It consists of multiple constituent machine learning models. And of course, there are weights on all of these models. And we're constantly trying to improve the model for relevance, making sure that the recommendations we show are actually what people want in terms of those they're actually going to connect with and talk with. Each of these model updates are rigorously tested, of course, with a randomized rollout known as an A/B test. And this is what is exciting for us because these A/B tests on the PYMK product induce as good as random variation in member social networks. So how does that manifest? Here's an example of a social network structure. When you have a PYMK A/B test that is launched, there are some members that get triggered into it, meaning that they go on the PYMK tab and then they get access to the recommendations. And so when they do that, they get access to either the A version or B version of the product. And so in red here is a version of the algorithm, which is recommending more strong ties. So strong ties are connections that you have that tend to be closer. So to simplify, they're folks like your classmates, your immediate coworkers, your family, those with who you interact with a lot. And weak ties are your acquaintances or professional connections, folks who tend to span lots of diverse networks, folks who you don't necessarily keep up with on a day-to-day basis, but those who tend to be important in terms of your professional network. And so there were some versions of the PYMK algorithm which were recommending strong ties. Those are the versions that you see in red here in this plot. And there were other versions that were recommending more weak ties in blue here. So that in turn leads for people to connect with different kinds of ties. So the folks in red are connecting with their stronger connections, and those in blue are connecting with some of their weaker connections. And that's the kind of randomized variation that we're leveraging in this work. What we have to be careful when we're talking about network data, because the way you're modeling the data is really important. So there are two ways that we were looking at within this work of how you aggregate network data for the sake of your analysis. So one is known as the edge level and the other is the node level. An edge level analysis means your data set, each observation is an edge, meaning each observation is a dyad of two people connected. And a node level analysis means that each observation corresponds to a unique member. So it's not a dyad, it's an individual person. And each one of these levels of aggregation has its strengths and weaknesses. In terms of the edge level, what a huge advantage is that there's direct attribution between edge characteristics. So whether an edge is weak or strong, and a job outcome. So whether this edge actually helped. So whether this particular connection actually helped someone find a job. And the other thing is that because you're modeling the edge outcomes directly, you're able to potentially obtain a more flexible relationship between the edge characteristics and the outcome you're modeling. Edge data, by virtue of it, being a dyad, there's a lot more data for the same number of members, and depending on your model, that could lead to higher power. A huge disadvantage of edge level data is that the sample that you're looking at, which is the number of edges that were created during your experimental period, is an endogenous outcome. So it's not the observations you're seeing are not ex ante fixed. They're a product of the experiment itself. And so you need to have an appropriate selection model to correct for this. And so you would need some kind of parametrics there. Now, talking about the node level, this is a super clean identification in terms of when we're talking about our causal inference, because the instruments, that is your PYMK A/B tests, are randomized exactly at the node level. And so when you have data at the node level, it's super clean. You don't need any control variables, for example. The problem with node level analysis is that you have to bin outcomes. Specifically, you have to bin edge level outcomes in some kind of way, because you're collapsing data from edges into their constituent nodes. The other issue, of course, is that because you're aggregating, as well as because now your level of analysis is a smaller level of analysis than an edge, this might lead to lower power in terms of detecting the effects you're interested in. So there are trade-offs for both, and that's why we actually do both kinds of analysis in our work, just because we think there's strengths and weaknesses to both. What are the exact model specifications we're using? So we had 2 waves of experiments in our data. We had a 2015 wave of experiments where we were looking at edge level outcomes. We had edge level data here. And so we were using an IV regression specification, where our instrument was, of course, the PYMK A/B tests. These A/B tests were not just A and B; they had multiple variants, 6 to 7 variants, and so we had control variables which were accounting for the kinds of selection that we were talking about. We had controls at the ego level, so at the level of the person sending the PYMK invites, and at the level of the person receiving those invites, as well as edge characteristics themselves, such as the strength of the edge. The characteristics such as whether they were the same gender, whether they're living in the same place, they went to the same school, and so on. The endogenous variable that we're interested in is the tie strength. In this specification, measured by 2 measures. One is the interaction intensity, which is a measure of how much are 2 people, I and J. I is the one who's sending the invite, J is the one who's receiving the invite. How much are I and J talking to each other? And then we have another measure of tie strength, which is the number of mutual connections that I and J share before they created the connection. And the second stage, we're modeling job transmission. Job transmission is essentially a measure of whether after connecting with J, me being I connected with J, and a year later, did I end up joining J's firm? So that's what job transmission is. It's a measure of, how did you leverage your social network to get this job? And we could model the tie strength in the second stage, either as is, or using a piecewise linear form to get at nonlinearities in that relationship. And then in the we did another wave, just because we wanted to also do a node level analysis. And so in the 2019 wave, like I said, the node level analysis tends to have lower power. So we waited and we got a lot more data in terms of the number of members. In the 2015 wave, we had about 4 million members. In the 2019 wave, we had about 16 million members. And so that was a ton more data. And this was a node level specification, so it's not at the edge level. And here, our endogenous variable, we had 2 endogenous variables. They were the number of weak and strong ties that were created during the study period. And the outcome this time was the number of job applications that a member sent out during this period, the applications that they discovered and that they sent out. For network data, it is essential to think about SUTVA violations. SUTVA is, of course, the assumption that there is no interference between experimental units. The interference is always a concern with network data, but in our setting, we have reasons to believe it was at a minimum for multiple reasons. One is by construction, in our edge level modeling, the edges that we included were what we call ego-initiated edges, which means that they were edges that I had sent out an invite to J, which means this edge will only show up for me, it won't show up for J. And so that's one way in which we're making sure that my actions as an ego does not affect the way we're modeling the alters who are receiving my actions. The other thing that's important to note in these tests is that we noticed empirically that these tests happen to affect the connection requests that egos, meaning those who receive that particular algorithm, send but it did not affect the requests that they received. So that's another channel through which interference was mitigated, because the effect of accepting connection requests from those from other treatment arms than myself was on balance equal across these different variants. The other important thing is that some of the metrics that we're looking at, such as tie strength, they're not individual level metrics, right? They depend on the network themselves. So an important thing for our model, for our modeling, was to make sure that all of these measures of structural tie strength were before the treatment. So essentially, you've had your network frozen before the treatments were applied, just for the sake of making sure you measure all these tie strengths. And of course, you can measure tie strength of two people who are not yet connected. And then once you have that, this kind of modeling makes sure that if one member responds to the A/B test and creates a new connection, it doesn't affect the measures of tie strength of other people, because this has been frozen before the experiment. And finally, in terms of, if my actions affect the kind of recommendation lists that other people receive, the good news is that the PYMK candidate recommendations list is massive. So me sending a request means that the other person will quickly, even though I won't show up in the other person's requests, in their recommendations list, there's someone like me who's quickly substituted, because that space of the potential edges is just massive. So to summarize, this work that we undertook was the first large-scale causal study of its kind. We had data spanning 2015 through 2019 from LinkedIn. During this period, we saw the creation of 2 billion new edges, 2 billion new connections. And also we saw 600,000 new jobs that were created on the platform. And so we could follow the A/B tests on these networks, see the kinds of changes in the composition of member networks that they induced, and in turn find what their association was with job outcomes, such as the number of applies and mobility. I think this is a point for me to pause, because that was a lot to take in, and I would be super curious. I might take some questions, a couple of them.
We have not received any questions so far. I think that people tend to ask questions when you ask for questions, so we don't have anything already open. So you can continue, and we can bring questions to you afterwards.
Okay, that sounds great. Let's continue then. So now I'm going to talk about the empirics. That was a lot of methodology. What did we learn from all that setup? What kinds of networks matter? So with this observational study design, and this was observational, I don't know if I mentioned that, because these A/B tests that were run were routine A/B tests that the PYMK product was running on their own. And what us, the researchers, did was that we happened to go back and notice that, hey, this kind of variation can be super useful for us for the question that we're answering. And so we essentially, quote unquote, harvested randomness, as Dean would put it, and did this analysis. The most interesting thing is to look at the difference between the left and the right plots, the left on the red and the right in blue. Left is a correlational study, so the kind of IV specification that I mentioned for the edge level regression, instead of doing an IV, just do an OLS for that same specification, which is you don't instrument for the endogenous variable. And then in the right is, of course, the IV specification. And we're seeing something really interesting is that on the x-axis where we have tie strength, in this case, the number of mutual connections, and on the y-axis is the probability of a job transmission. That is the probability of someone connecting with someone else and then joining their firm. We're seeing that in an OLS model, and what's interesting is that this is in keeping with that Facebook study. We said this is the same kind of overall trend that we saw, so it was nice to see that replication, is that in a correlational study suggests that the stronger a connection is, that is, the further to the right on your x-axis you're going, the more it is that you're seeing job mobility, the higher it is that you're seeing job transmission. Whereas when you change the study design to this IV study that this IV model that we were looking at, we actually see almost the opposite, where the strongest connections are actually the least helpful. And we're seeing an interesting pattern where there's an inverted U relationship. The weakest connections, meaning the ones with the mutual friends being at the lowest, are second helpful, but the most helpful seem to be the ones that are hitting some kind of sweet spot around 8 to 10 mutual connections. There's something about that which suggests that, you know, we're not really seeing the best gains from the strongest connections, but somewhere in the moderately weak connections. We also looked at many different other measures of tie strength. So interaction intensity, meaning a measure of how many messages were being exchanged between members, is another one. And again, interestingly, in the correlational study, you're seeing that the stronger the connection, that is, the more messages they're exchanging, the more you're seeing job transmission, whereas with our IB design, we're seeing the opposite, in fact. And this is the same kind of pattern we're seeing even with using another measure, which is the relative number of mutual connections, which is the number of mutual connections divided by the number of total connections that Ego and Alter have. And there too, we're seeing that weak connections matter more for job outcomes. We were interested in trying to dig a bit further. It's good to know that, you know, weak connections or moderately weak connections matter, but how is that manifesting in some ways? So one way we did that was looking at heterogeneity of this coefficient in terms of the industry that members are in. So we at LinkedIn had a classification of about 140 industries that members could be in. And then we used measures from the literature of how these industries fare in terms of different metrics of technology. So things like, how much are they using information technology? What is their software use like? Are they using a lot of automation? Are they using artificial intelligence, and so on? And so we did a binary. So we took these 140 industries, we had a measure for each one of these different measures of technology intensity. And then once we had that, we went ahead and then binarized those in terms of those industries that are at the top of these measures and those that are at the bottom. And then we looked at heterogeneity of these weak tie and strong tie effects by these industry measures. And what we're seeing here, and this is the 2019 data on job applies, is that across all of these measures, we're noticing a consistent pattern, which is that those industries that are at the top of all of these measures of high-tech use and intensity tend to be the ones where the weak tie premium is at the highest. And so in these industries that have a lot of high tech, you know, it matters. Those who are connecting with weak ties are discovering and applying to more jobs than the corresponding comparison for those in more traditional sectors. And I think one way to think about this is that the industries that are at the top of these rankings tend to be moving at a faster pace in terms of their innovation. And a lot of the traditional literature of weak ties, they suggest that weak ties serve as a conduit for information. So that's another way that we can look at this figure and say, oh, perhaps that's just what's going on, is that those that are at these top of these rankings, it's really important to keep up with the latest and greatest. And so weak ties help you do that much more efficiently than do strong ties. Whereas those that are at the bottom, such as in industries such as aviation, transportation, that weak tie advantage is not as much. And perhaps the other benefits that strong ties bring, which is the closeness, their ability to vouch for someone, and so on, those tend to outweigh any informational advantages that weak ties are bringing. What's really interesting these days, I think, is heterogeneity by remote work. And so we had another classification of industries by ability to do the job from home. And again, we're seeing that weak ties matter more in terms of job mobility, discovering and applying to jobs than industries in which work from home is not that common. Now, what implications does this have for the labor market? our work suggests that weak ties are important, across a range of measures of tie strength and across a range of job outcomes, whether you're talking about actual jobs held or jobs that were discovered and applied to. We're finding that weak ties or moderately weak ties tend to matter more than strong ties. So they help people discover jobs and they help people find jobs. And they likely serve as a conduit for information flows, whether information on the job, information on the latest R&D, information, other industry relevant information. Weak ties seem to serve as the conduit for that, and that's why they matter a lot. And so in terms of an implication for job seekers, we always like to say that, it's really important to lean into your weak ties and your second degree connections on LinkedIn. The stuff about remote work is also super interesting. And I think we have to be thinking about this a lot these days because our work shows that weak ties matter a lot for those who are in industries that are doing remote work. At the same time, there's lots of work that's coming out, whether it's from Microsoft or MIT and other places, that increasingly during fully remote work, weak ties are actually super hard to create and maintain. And so this is particularly problematic because we know that those who are doing remote work benefit a lot from weak ties, whereas it's this remote work itself that's making it very hard to actually create and maintain these ties. There's a sense that strong ties are great for execution work. When you have strong ties, you can do execution work, and weak ties are great for ideation work. So all of these effects put together give us, the sense that we should likely expect lower innovation, productivity, and mobility on average from this remote work revolution. And so my takeaway from the reading of all of these studies and our own work is that hybrid work is kind of the place to be. It may lessen some of these negative effects of fully remote work. And so, employers, whether it's in academia or in industry, it's really important to have a strategy to make sure that we're having serendipity occur, because weak ties are that conduit to serendipity. But of course, hybrid work isn't like a well-defined thing. It's just saying it's not either of those extremes. It's not the fully in-person work that we were doing back in the day, which of course has all these disadvantages, which is why remote work is attractive to people. But then fully remote work has all these disadvantages that we're discovering over the course of the pandemic and beyond. And so we know flexible work is a place to be, but designing effective flexible work is going to be where the gains are going to be at for the workplace. And so a question to think about is how does serendipity look at your workplace, and how you make sure to induce that and to keep up with that in this modern hybrid work environment. Okay. Finally, just a couple of thoughts on what I think could be interesting avenues for work that's coming up next. In terms of future research, I think one place that from the statistician or network science point of view would be really cool is for a network robust inference. In international trade and stuff in economics, there's an approach called dyadic clustering. Essentially, when you have edges, it's a way of accounting for correlations in the error terms in these edge level regressions that account for the fact that you have network data. And because traditional one-way clustering, where you're only clustering at the ego level or at the ultra level, might not sufficiently account for all of the correlations occurring between edges. This is a promising approach. I don't think this approach has as yet been generalized to endogenous variable settings, so IV models in particular. So I think having that for IV models would help tremendously. Another place I think where we could use a lot of innovation is doing IV models for edge regressions. Like I'd already discussed, edge data sets are a survival sample of those edges that were actually recommended and created. Of course, there's a whole number of edges that were recommended, but that were not created, and of course not included for tractability reasons, because those edges that were not actually created, or a much larger fraction than those that were created. So we need methods to account for this kind of selection bias of only the edges that were created that exist. So how can we deal with that appropriately? And finally, from the empirical point of view, I think it would be super interesting for those empirically oriented to study, the mediation analysis of weak or moderately weak ties. Our work suggests, 8 to 10 mutual connections is somewhat of a sweet spot for job mobility. But of course, there's nothing special about 8 to 10 connections. It's just sort of a symptom of what's going on, what might be helpful. Some folks say it might be what are known as bridging ties. Bridging ties in particular are those ties that tend to effectively bridge communication between two diverse networks or two diverse clusters of networks in a social network. Is it that? Is it something else? What is it about these ties that make them so effective? What are their characteristics? What are the mechanisms through which they're helping? Just concretizing all of those things and quantifying them, I think would be super helpful in the study of weak ties and social networks, broadly speaking. I had one last slide, which was to, because I was told that industry talks are not as common at this forum. So I thought I might talk about what our team, I'm in the LinkedIn experimentation science team. What is some of the work that we do beyond the one I just discussed? Here is a snapshot of some of the work that we've done in the past year. We've looked at fairness in A/B testing. So I'd already talked about some of the work that we did with the Project Every Member, where we target distributional shifts. We do other things like looking at outcome tests for ranked lists. When you have a recommender system and you're ranking a number of folks based off of a certain trait, how do you make sure there's fairness in these rankings? And then we also have other work that's on how do you do inference when a certain metric is of the form of a min over a certain number of groups divided by the max over a certain number of groups. How can you deal with that? We're interested in causality in marketplaces. LinkedIn is a marketplace company. We have lots of different marketplaces, whether it's jobs or people or our advertiser business. And so when you have marketplaces, how do you actually account for causality there? And we have papers with respect to that. We're super interested in privacy and how do you do A/B testing with privacy? So when you have a certain A/B test that you're trying to measure and you want to make sure the outcomes across certain groups are sort of equalized or not getting too far apart, but the group identifier itself is privatized because it's a highly sensitive variable. And so it's not the actual variable that's the ground truth, but a kind of noisy version of it. How can you do traditional A/B testing? And we have papers on that. And finally, a perennial concern for us in industry is how to make sure you have optimal variance, which means the lowest variance for the kinds of outcomes you're looking at, and we have a paper based off of that as well, and much more. So I will close now. Thank you so much for your time. You should definitely read the paper if you're interested. Here's a QR code that lets you do that. And I think I will end it here. Thanks again. I'll pass it on. Maybe this is a time for questions, if there are a couple of questions before we hand it off to Dean.
It's a great time for questions. Thank you for your presentation. So maybe we have a few open questions. We can take a couple now and then go to Dean for the discussion. So I guess let's start with a somewhat more technical one. How do you, what are the credible levels of the bars? Are the beams of different plots correlated? So I think that has to do with uncertainty quantification. And it came up when you were plotting your estimates with the red and the blue.
I see. Yeah, that's a good question. So the plots that I showed you were a bin scatter plot. So you take the endogenous variable, your predicted endogenous variable for your IV regression, and then you do a bin scatter with the outcomes. It's a good question as to whether the level of the bars is accounting for all of the uncertainty. At one point, we experimented with doing a bootstrap of the same thing rather than just doing a bin scatter that comes out of CAM software. And the results were generally similar, so we didn't pursue that further. But what I will say is also that The more important question is, how do you appropriately account for non-linearities in this relationship between the outcome and the tie strength? And what we do is we use a traditional linear IV regression, but then we do a piecewise linear fit to it. So we have a term that's just the tie strength, and then that's another term for a high level of that tie strength. And then we do a traditional IV regression, and those confidence intervals are, of course, the ones that we're most interested in when we're reporting estimates.
Great, thank you. So maybe we can take one more. So could it be the reason why you see weak connections might mask the fact that individuals might actually be really close friends and interacting on other media, such as phone calls or emails or meeting in person, and your data are completely blinded to this? In other words, is LinkedIn notion of strong or weak ties the relevant network notion for strong and weak ties?
This is a very good question. I think when you're looking at strong and weak ties, it really is important to know what outcome you're trying to measure and what effect it is that you're interested in. In our case, we were interested in job measures. And, I personally think that, LinkedIn being the biggest professional network of all, of the world, it's not a bad place to start when you're looking specifically at job outcomes. And actually, the penetration of LinkedIn in certain industries is near perfect, at least at the entry level. So whether you're talking about finance or high tech and so on. And so a lot of the activity that you're talking about in terms of job postings and job held, LinkedIn data is near perfect for that. I think in terms of both the connections that people have and in terms of the keeping up to date the LinkedIn profile. So that's, I think, yes, that's there. It is a very good question in terms of other outcomes. But yeah, I think ours is one study of many that'll come, in the way, and we provide strong evidence for what LinkedIn data represents best.
Great. So I think we'll stop here for questions, and the questions will remain there if you want to answer them if you have time, and we can move on to Dean for the discussion. And we will forward these questions to Karthik afterwards. So if you want to follow up with him.
Okay, it's really my pleasure to be commenting on this paper. You can all see it. So this is a particular pleasure to comment on for a couple of reasons. One is that I've been kind of following this project a while because obviously this is quite the undertaking. That all the experiments that were conducted, some time ago, and you have to wait a little while to realize some of these outcomes, right, to see how people are changing jobs, et cetera. So I think that's just, a really exciting part of it, the kind of work that goes into this and then seeing this project out there in the wild. Another part is because I do a lot of work on causal inference. So I think this is interesting, and there's some challenging questions about how to do this kind of analysis. And then also because I'm doing a lot of research on weak ties and long ties myself. And so I have a couple papers in that area. So I think, I know that many of us who have been working papers in this area or papers under revision at the moment have been rewriting our introductions, conclusions, and maybe even broader swaths of the paper as a result of this work. So, so first, I just want to say that this is hugely impressive work. Of course, since I only have a couple of minutes to comment, I'm going to focus on, kind of little things that I have questions about or that maybe are interesting directions for people working in this area. So I'm not going to say a lot more about just kind of how cool this paper is. So I'm going to say a little bit about the idea that this is kind of this interesting meta-analysis of a bunch of sort of fat-handed interventions. Talk a little bit about just how weak ties are defined here. And then finally, really dig into this issue of the edge level analyses, which is where I kind of have some questions of does this methodology make sense? So this plot on the right is from some work that I did a while ago, and I think is representative of the idea that internet companies are often running tons of experiments. Each point here is one newsfeed experiment with about 20 million users in it, right? Affecting two different variables. So one of the things, especially when we're running like routine product experiments, is that a given experiment might affect multiple things at once. It's kind of a fat-handed intervention. Like we try to maybe increase this one thing, but it increases a bunch of different things, right? So that's kind of an interesting feature of a lot of these experiments. It often can make it hard, even in designed experiments for science, to learn about the specific mechanisms via which some intervention is having its effects, because it may be happening via multiple mechanisms. But hey, if we have a bunch of these experiments lying around that kind of, each one is sort of fat-handed, but they're fat-handed in different ways, maybe we can learn some things from that. So we can pool many experiments to decompose these effects. And that's sort of what I see this team is doing here, is that they've said, look, a single one of these experiments, or maybe even two of them, wouldn't be necessarily enough to tell us what we want. And also, these kinds of experiments are very expensive to run. These aren't run just for the academic research. We have a lot of these lying around, use this independent variation, right? So I think here, this is one view of the kind of first stage of this analysis, right? Is what's the effect of a bunch of these different variants on producing more ties overall, more weak ties or more strong ties, right? And so, each one of these experiments is potentially affecting multiple of these things at once, right? Some experiment could just sort of, from LinkedIn's perspective, maybe be better, and that it's just helping people find people they know and form connections with them, right? So it's producing more of all ties, right? Whereas another one might, actually not really affect all ties, but kind of shifts the mix in some way, but maybe it shifts the mix on multiple dimensions. So I'd say, I think this is kind of an interesting direction. It's also challenging because each of these PYMK experiments but potentially affects formation of weak versus strong ties, ties that with common university or workplace. It might be that that's one of the things that some new model does, that says, oh, we're going to, emphasize places, people that, you might have worked with or something like that, right? Or change how that's estimated, right? Ties that have maybe more or less active alters. Sometimes these online services try to use PYMK-like features to bring people back to the platform. Maybe the person being recommended as someone you should connect to is somebody who hasn't been active on LinkedIn in a while. And by suggesting them, you might resurrect them and they'll come back, right? So there's so many dimensions here. And I think obviously, strong and weak ties are two of the really important dimensions for this work. But we might also think about whether there's other dimensions and what can we do methodologically. So I think one thing to just note is like the kind of modern perspectives on IV that we get from one of the organizers here allow for latent heterogeneity, so that what the quantities that we're identifying through these kind of IV analyses are defined for some latent population, but are still interpretable as causal effects, even in the absence of strong parametric assumptions. Mainly, those things don't apply to multiple endogenous variables. So if we're doing this kind of randomization, harvesting of this randomness, right? What are we getting? My sense is that if you look at, say, the Mendelian randomization literature, they mainly just start assuming linearity and homogeneity again. So is there any way to get out of that? Two recent entrants in this literature that maybe are sort of discouraging are these two papers, one about noncompliance in a kind of experimental setting, and another one on the idea of just weird weighting that happens when you start doing regression with multiple treatments. So I think this is maybe if all of a sudden we're going to have all these experiments and we can do these IV analyses on, what does that do for our perspective on what IV is actually estimating? Okay, second, I want to just a little bit about the conceptualization of strong ties and weak ties here. Maybe this is more for the social scientists in the audience, right? So I think, after Granovetter, we have this idea that strong ties, these are like high intensity or intimacy ties, are often embedded in closed triads. That's not how they're defined, but often they're embedded in closed triads. Whereas weak ties are more likely to be part of open triads. Weak ties are more likely long ties, and that they connect us with people we're not otherwise connected with, or we have few other connections to. And so that's part of what maybe makes them valuable, is they provide access to novel, non-redundant information. And so, other social scientists like Bert have described this as providing information advantages because we're getting access to novel information through these weak, or perhaps more properly described, long ties, and that they're local bridges or sort of low embeddedness ties. That's something that, like, the present paper is a little bit kind of confusing on, and I know actually it can be very challenging to write things for a science paper where it's all kind of compressed together. But at some points in the paper, weak ties are ties that actually have low embeddedness. So I'd think of them as long ties. They're ties with people you don't have many mutual contacts with. You might think of them as kind of local bridges of some kind, right? But other analyses use interaction intensity. And I think overall, we might think of these as just being sort of independent factors, or things that actually you should somehow consider jointly in some way, right? Actually, some work by one of the authors of this paper, Sanana Rall, thinks about the notion of bandwidth, and that actually, to get access to this novel information, you might need this interaction intensity. So I think that's a really interesting further direction. From a more methodological perspective, I think it's challenging to think about how should we analyze the effects of having weak versus strong ties if this is sorry, is that me doing that? How would we analyze effects of weak versus strong ties if this is measured via frequency of interactions, when basically we only see the frequency of interactions once the tie appears, right? So I think that's challenging. My sense is that the solution in the paper is either to analyze things just in terms of the structural measure of tie strength, basically being short versus long ties, or to actually form ties during the experiment. And that brings me to the last thing that I want to discuss, on which I would say is also sort of the most directly critical aspect of my commentary. So the analyses in the paper really fall into two categories. One are these node level analyses. Here, as Karthik mentioned, the data are one row per user. These users were randomly assigned to different PYMK models. This seems like exactly what we want, right? And I kind of know what's going on here. So maybe there's like some complications because there's maybe some interference, and we got to be boss to some network dependence. And I think they do some reasonable things there. And also, I think it probably doesn't end up mattering a lot for this particular setting. So I think this is pretty straightforward and credible. The other set of analyses are these edge level analyses. Here, the data is one row per edge or tie, which we could use that interchangeably, that forms during an experiment. That doesn't necessarily mean that that tie was caused to form during the experiment, but we do observe all of them across the different experimental conditions. And we could think about how some of these experimental conditions are causing certain ties to form. So kind of my question is like, what's going on here? What is this analysis doing, right? So if we say are looking at these results where we're looking at the probability of job transmission given a tie, and then we have, an OLS regression, which is sort of looking at the actual interaction intensity of ties that form during experiments, and then how that's correlated with probability of job transmission. That's on the left. And on the right, we have the IV analysis. And so here's this interaction intensity that's been instrumented for in some way, but these are all edges that form during the experiment. So I think conceptually, I have trouble figuring out what are the counterfactual that are involved here. So you're analyzing edges that form during the experiment. Here on the right is what the first stage looks like for the 2015 edge level analysis, right? So each of these variants is like shifting how many mutual connections or interaction intensity there is a set of edges that form during the experiment, okay? So what happened to all the counterfactual ties that didn't form for the people who were assigned to variant 3, but would have formed had they been assigned to variant 4? They're not in this analysis. I think we at least want negative samples here. Karthik mentioned that, like, actually there's way too many negative samples, right? These are, there's like order n squared negative samples because this is a sparse network. But I think we actually only need some downsampled set of these in some way to work. Still doesn't necessarily solve the problem of trying to measure it as interaction intensity during the period of the experiment, because maybe we're not sure how that should be filled in. But for the mutual connections analysis, it seems like we could do that. You can think about a very simple case here, like say you only had a binary treatment assignment and the treatment causes more ties, only weak ties, to form. The outcome is then job transmission. One thing we might note about this is there's potentially negative dependence within the same ego here. If you're a given person, you can't just keep collecting jobs. you can only kind of get one job from one person. So if we kind of consider this case, what are the results that we get here, and what should we get? Which I think raises some questions about just fundamentally, what is the estimand in this kind of edge level analysis? And I think there is something interesting here because, this is a way of really digging into some of the details of these specific edges that form, but I'm not quite sure how to make sense of the present analysis. So I just want to conclude. So again, I think this is impressive work, especially for those of us who are, have been either doing it sort of this general kind of thing, analyzing lots of these big internet experiments, or thinking about long ties and weak ties. This is hugely important work. I'd say it'd be nice to think about what we could do for methods for many endogenous variables, just thinking about for the statistics and causal inference community here. Can we learn jointly about all these different kinds of endogenous variables, some of which are then going to be measures of network structure and interaction intensity in the network? And I think we really need methods for learning about the effects of network structure. This team has done some impressive work in this direction and has really kind of tried some interesting things, and some things that I think are quite robust and credible, the node level analyses. But this is an area that needs some more active attention. Anyway, I think really cool stuff, and it was my pleasure to discuss it today.
Yeah, thanks for the nice discussion, Dean. Karthik, do you want to respond to some of the questions?
Dean raised so many good points. I don't think I'll be able to address every one of them, but I've taken a note of every one of them, and I really appreciate all of the wonderful, thoughtful comments. I'll quickly address a few thoughts that came to my mind. How do we think about what it is that we're measuring in these things? I think for me, the question of counterfactuals came up. What is the counterfactual? And especially given that there's all these different PMK variants and each one of them is doing a different thing, what are we trying to really get at? And I think, for me at least, the way I think about these estimands is we're looking at the causal effect. Whenever you're looking at causal effects, you need to know what the intervention is. And here the intervention is the creation of a new tie, because that's just directly what stems from the showing of these recommendations. And so the target estimand for us is really the causal effect of the creation of a new tie and looking at heterogeneity of that quantity based off of these edge characteristics, whether these edges are weak or strong. So think of it as like the causal effect of creating a tie that happens to be weak or strong. Now, that's where it's really key on what does that mean that it happens to be weak or strong? And I think that's actually a strength of this work. It means that this is a tie that has been created and it's a weak tie and it happens to be weak based off of this network. But just because it happens to be weak doesn't mean it's the only thing that defines it is it's weak as compared to the strong tie. The thing about being in a network and the thing about what makes weak ties so important is just the context in which they're situated. So these weak ties bring a whole bunch of goodies to them, including the, all of these different aspects of them being in diverse parts of the network and being connected to all these different folks and the information that they bring. So I think that's an important point to make. The other thing, I think the point about the edge level regressions is really key. It's really important. Yeah, negative samples is something that I think would help. We hadn't done that, but I think future work could and should. What we did try to do was try to experiment a little bit with some kind of Heckman style selection models for the edge regressions, just because, like I said, it was a survival sample. But ultimately we chose not to do it just because it brought so much more parametrics, and ours was a much more empirical take. But I do think that's why I outlined it in the future work section, is that it would be really helpful to have theoretically grounded work on this is the model, this is the estimation model that we're coming up with, and this is what the estimate precisely means in that model. So I think there's that would be really helpful for the edge level of regression stuff. The points about many endogenous variables, super interesting. I'm personally going to have to explore that literature further to learn more about what's going on. And in terms of harvesting randomness across multiple different interventions, the good thing for us is that our experiments, both the 2015 and the 2019, were of relatively short duration. And even though they had multiple treatment variants, we would imagine that, although we're doing this kind of IV analysis that's aggregating across all the effects across all these different things, based off of the fact that they were individual experiments that don't have a lot of interactions with other things going on, there weren't a lot of simultaneous experiments. We feel like they were all pointing broadly to the same directions. just by virtue of the fact that they were short duration, they weren't a lot of parallel experiments being run. But I do think that it's something to be cautious against. I think, yeah, mainly those were my thoughts. I think there was a lot more. I'm going to go back to Dean's slides and think harder about some of the very excellent points that he's raised. But thank you so much for the time. And I know I should stop because we're at time.
Yeah, thank you so much. Yeah, I think I'll quickly wrap up. Yeah, first, thank you so much, Karthik, for the very nice talk, and Dean for the interesting discussion. Yeah, next week we're going to have a talk by Julie Jose, I hope I pronounced it correctly, from INRIA. We'll talk about causal inference for brain trauma, leveraging incomplete observational data, and RCTs. Yeah, thank you all for coming. Hope you have a great week, and see you next time.